All right, thank you for that introduction, Beatrice, and thank you all for being here. I'm really happy to get a chance to speak to you today. So I'm going to give you a brief introduction here to powder diffraction. It's going to be an introduction to powder diffraction, but there'll be elements of an introduction to Rietveld refinement as well. We will briefly look at the history of powder diffraction. I promise I won't bore you too much with history, but just a little touch. We'll look at a variety of applications of powder diffraction and Rietveld refinement to give you an idea of how these things can be used in your research. And finally, we will look at the main factors influencing Bragg reflection positions, intensities, and peak shape so that you can better understand your data and how you can make optimal use of it in your work. So the first question is, what is powder diffraction? When we refer to a powder, we are generally talking about a fine-grained material with crystallite sizes ranging from microns to nanometers. Hopefully everyone should be familiar with Bragg's law. Bragg's law simply describes the condition for constructive interference between scattering from adjacent planes. And when 2D sine theta, or this little area in red here, is equal to an integer multiple of wavelengths, that is your condition for constructive interference, and that's when you get diffraction. In powder diffraction, typically we shine X-rays on millions of crystals, and the individual diffraction spots from each of these crystals merge to form two-dimensional rings, like this on a detector. This is what we would call an ideal pattern here on the bottom left, or an ideal powder. You can see if you have a mixture of crystallite sizes, what happens is you get a grainy powder, like the powder in the middle. If you've got larger crystallites that are actually quite coarse, typically larger than 5 or 10 microns. And if you diffract from a large single crystal, like we have on the bottom right here, you just get a pattern of spots that's representative of the specific orientation of that crystal. Powder diffraction is a really powerful technique, and there's a lot of information content and numerous applications. You can quantify different crystalline phases in a mixture. You can solve and refine new crystal structures of interesting materials, and you can gain information about microstructure, things like crystallite size and crystallite strain. And with the advent of the pair distribution function method, you can even look at local structure in poorly crystalline and amorphous materials with no long-range order. And Graham will be talking about this later in the week, I believe on Thursday. So just briefly here, we'll talk a little about history. The main point here is diffraction is now over a century old, and powder diffraction has been around since the very beginning. The very first diffraction cameras were designed independently by Debye-Scherrer and by Hull, less than 5 years after von Laue first demonstrated diffraction. It was about another 20 years before the first diffractometer was designed by Donald Le Gallais. By 1941, the precursor organization to the International Center for Diffraction Data had been founded, and they were already starting to compile diffraction patterns together for sets for phase identification. This is a schematic of Hull's camera design. You'll see it's very similar to a typical capillary geometry experiment that we would perform today with an area detector, except that he was using photographic plates and a molybdenum tube X-ray source. Hull talks in the beginning of his paper about how the methods of von Laue and the Braggs required reasonably large individual single crystals, but for many materials, sufficient crystals either weren't available or they were very difficult and time-consuming to actually prepare. And he was already beginning to discuss practical considerations like rotating the sample in the beam in order to obtain as many different crystallite orientations as possible. Cameras were used extensively in the early days of powder diffraction, but the first powder diffractometer was designed by Le Gallais in 1935. And this diffractometer didn't have any parafocusing capabilities, so the intensities were not very good. You can see each step in this pattern for potassium chloride took about 4 minutes to collect. Lagelle actually went on to work in the space program, and he eventually wrote entire books on like space physics and ballistic missiles and reentry vehicles. He literally went on to become a rocket scientist. The creation of the Rietveld method was a real turning point for powder diffraction. Prior to the Rietveld method, powder diffraction tended to be used as a qualitative fingerprint for crystalline materials. The Rietveld method provided the basic tools that were necessary to unlock the really high data content of powder diffraction patterns and to begin to make more quantitative use of it. Rietveld initially used the method on neutron diffraction data because neutron diffraction has a simpler peak shape than X-ray diffraction data. So it took a while for people to realize the full potential of the method. Applying the Rietveld method to X-ray diffraction didn't occur until later in the 1970s. And since the 1980s, equipment and software and methodology have consistently continued to improve. So techniques like structure solution, PDF analysis, and synchrotron data collection are becoming much more common and much more routine. Powder patterns always suffer an inherent loss of information compared to a single crystal diffraction experiment. With a single crystal diffraction experiment, what you do is you collect a pattern of spots at many different crystal orientations. You might collect hundreds, even sometimes thousands of different patterns by rotating the crystal in small steps and collecting a new pattern at each step. The intensities of the individual spots, or the sets of crystalline planes, can be measured accurately and with really high redundancy. With powder diffraction, all the crystal orientations are collected simultaneously. Hence, we get this pattern of rings, which you can then reduce to an actual 1D powder pattern. And they get merged into one image. So invariably, this leads to a major loss in the information content due to peak overlap. This makes powder diffraction a more straightforward experiment than single crystal diffraction in some ways, but maximizing the information is a lot more challenging. Due to the issues with peak overlap, the majority of early powder diffraction work was qualitative in nature, predominantly fingerprinting and phase ID type applications. Quantitative methods tended to use a small number of isolated peaks, rather than using the entire diffraction pattern. And structure solution in the early days with powder diffraction was very rare, and it was mainly restricted to high symmetry compounds and was kind of considered a major task that was only undertaken by small numbers of experts. Two things were required for the development of the Rietveld method. We needed enough diffraction theory and physics to be able to sufficiently describe the patterns, and we needed powerful enough computers to implement the method. And these two criteria converged in the 1960s. Rietveld's two seminal papers, which describe the method, from 67 and 69, are listed here. You'll notice he's actually the sole author on these papers. A third paper listed here from 2018 is kind of an interesting read. While Rietveld was the sole author on his 69 paper describing what would later be called the Rietveld method, he had significant input and discussions with some of his colleagues at Penn. And some of his former colleagues even go so far as to say the initial idea for the method wasn't Rietveld's, and the method shouldn't be named after him. But ultimately, at the end of the day, Rietveld was the first person who was able to implement the method using computer programming, and the rest is history. It's a very interesting read, though, that 2018 paper. So what is the Rietveld method? The Rietveld method is a least squares refinement method for powder data. It's important to emphasize that the Rietveld method is a structure refinement technique. It's not a structure solution technique. We will talk tomorrow in more detail about methods for some structure solution. In order to perform the Rietveld method, you have to have a decent starting model of your crystalline phases in your sample, and you also have to have an adequate description of the experimental geometry. And much of this talk will be devoted to helping you understand how the various variables associated with the crystalline phases and the experimental geometry influence the powder diffraction pattern. I mentioned earlier that there's a lot of information content in a powder diffraction pattern. Powder diffraction has traditionally been used to fingerprint crystalline materials, but it's widely used now in quantitative phase analysis, including quantifying mixtures with amorphous content, solution of new crystal structures, and determination of crystallite size and strain. And diffuse scattering can be used to analyze, or can be analyzed with a technique called pair distribution function, or PDF analysis. And like I said before, this can be used to study local structure in poorly crystalline and disordered and amorphous materials. Here's a few of the things we can analyze with the Rietveld method. Increasingly for modern materials, we want to study how they function in realistic operating environments to fully understand their behavior. And the high flux available from the synchrotron is particularly useful for conducting in situ or operando studies. That's one of the main advantages of using the synchrotron for powder diffraction. So I'm going to talk a little bit now about a few of the applications. Structure solution of new crystalline phases with powder diffraction has grown rapidly in the last 20 years, to the point where it is common, if it's not quite as routine as it is with single crystal solution methods. This crystal structure was actually solved using raw data that was deposited in the powder diffraction file database. In addition to the despacing and intensity lists used for phase identification, the powder diffraction file actually has thousands of raw data sets as well that are loaded in it now. And we use this one to solve the crystal structure of trandolapro, which is a common drug used for hypertension or high blood pressure. And we'll actually take a closer look at this structure solution tomorrow. One of the highest profile successes of powder diffraction and the Rietveld method was the structure of YBCO, which was one of the very first high temperature superconductors. The initial crystal structures of YCBO were obtained with single crystal diffraction, but they generally didn't agree with one another very well because YBCO is very prone to crystal twinning, which can complicate single crystal analysis. But multiple independent groups subsequently looked at YBCO with neutron powder diffraction, and they obtained consistent, correct crystal structures for the material. And oxygen ordering in the one-dimensional chains of the orthorhombic form of YBCO are critical to the superconductivity. Neutron diffraction is very sensitive to oxygen positions, more so than X-ray diffraction. So neutron diffraction was an ideal tool suited to solve and refine this crystal structure. You can even solve things like macromolecules and protein structures using powder diffraction. This is an insulin complex, which was solved by Bob, who we're lucky enough to have here today. And he's also the author of the GSAS and GSAS2 software packages. And he used synchrotron powder diffraction to solve the structure of this protein complex. This molecule has 1,630 independent atoms, and the unit cell is just enormous for people that are accustomed to small molecules. Bob did this over 20 years ago, and it still blows my mind looking at it, that he actually managed to solve this. Another big application is phase quantification. I used to work for a biomaterials company that worked on synthetic bone products, and our main biomaterial was supposed to be a two-phase mixture of what's called alpha tricalcium phosphate and calcium hydroxyapatite. Every so often, we'd end up with a batch with a third phase in it called beta tricalcium phosphate, which was forming at the expense of the alpha TCP phase, which was what we really wanted. And this was a difficult issue to solve because the elemental analyses from the precursor reactants we used to make the material that were provided by the chemical vendors were often inaccurate. So that actually hid what the real problem was. So we ended up using elemental analysis with ICP-OES, independent from the vendors, to determine that trace magnesium was what was causing the problem and causing the beta TCP to form. Powder diffraction has even been used to track the quality of products online, like Portland cement. This system provided a continuous flow. There's a continuous flow belt that brings the material into the diffractometer, and it has a curved strip detector, which you can see right here, in order to obtain the entire diffraction pattern fairly quickly. And I've shown the major phases here in the figure at the top right, but they were also able to quantify minor phases like calcium sulfate phases, like gypsum and hemihydrate, that were only present at 5% or below. And powder diffraction has even been performed on Mars. The Curiosity rover was equipped with a miniaturized XRD and XRF instrument called Kevin. And if you look at the schematic, really, the method isn't that much different than Hull's method, his camera from 2017, except the technology associated with the components is radically different. And this diffractometer uses a really clever piezoelectric vibrational device. So basically what they would do is they collect the powder and put it between two plates and vibrate it. And they use this in lieu of rotating the capillary like you do in a lab in order to get decent particle statistics and optimal random orientations of the crystallites. You can see here, using their piezoelectric vibration system, they're able to get pretty good random powder rings from very challenging and heterogeneous samples. And they were able to analyze complex samples from a number of different locations on Mars. And one of the interesting discoveries was the presence of a poorly ordered phyllosilicate phase, which could indicate that the material once underwent alteration by liquid water. A lot of information is contained in the peak shape and peak breadth of diffraction peaks. This example is part of a round-robin study to examine size and strain broadening across different laboratories. Shown here is a synchrotron diffraction pattern from the ESRF for unbroadened and broadened Sirius samples. And the increased breadth of the pattern on the right is mostly due to crystallite size broadening, although there's possibly a very small microstring component as well. And we actually have a tutorial this week looking at the data for those that are interested, or I can give it to you to try at home if you want. And many materials form crystals with very specific morphology or habit based on their crystal symmetry. Nickel hydroxide is a material that can crystallize in hexagonal platelets, which create anisotropic broadening in your powder patterns. You can see that some of our peaks are much broader than other ones based on the HKL indices and the Miller indices of the various peaks. And we can fit this pattern with a model which correlates that broadening information with the crystal symmetry in order to obtain average crystallite dimensions. And the average crystallite dimensions for these hexagonal platelets are shown here on the right. Some of the most challenging samples to work with are clays. I've been looking at clay standards from the Clay Mineral Society in an effort to improve my ability to actually try and quantify them. This is a Rietveld refinement of nontronite, which is a turbostratically disordered smectite clay mineral. And the pattern has really broad asymmetric features that's indicative of 2D materials. And Rietveld codes like Profx and BGMN have customizable scripting, which is actually capable of describing complex phenomena in like turbostratic disorder. And if you want to use Rietveld, a full Rietveld approach for clay quantification, you really need realistic physical models and advanced tools for clays like smectites before you can try tackling a sample like this. This is a nickel laterite sample with plenty of different phases, including at least 4 different clay minerals in there. And these types of samples are very challenging, and their analysis is very much a work in progress for me. So I mentioned before, Rietveld method is inherently a structure refinement method. It's not a structure solution method. So therefore, we need to have a reasonably accurate initial crystal structure for every phase. We want to have a very good characterization as well of our diffractometer. We want to know our instrument parameters very well before we start. And so to apply the Rietveld method, we really want to understand the parameters that control our Bragg reflection positions, our intensities, and also our peak shape and our peak breadth. This table provides a summary of some of the main parameters which need to be accounted for to properly model a powder diffraction pattern. While the key parameters are shown in bold, you'll notice that a lot of the additional parameters are also shown in italics, suggesting they can be very important depending on the circumstances. And as I've mentioned, there's a lot of information in the powder pattern, but extracting all of that information, it's not always easy. And we'll look at many of these parameters in a little more depth as we go through this presentation. There are a number of different possible experimental PXRD configurations, but there are two main geometries we're going to consider here. Bragg-Brentano geometry in reflection mode is the dominant method used for laboratory diffractometers, typically with a copper anode, but sometimes also with anodes like cobalt, chromium, or even molybdenum. Excuse me. Debye-Scherrer transmission geometry is a very common synchrotron and neutron diffraction geometry. And both geometries have strengths and weaknesses. You get more intensity from the sample using Bragg-Brentano geometry, but it's also prone to systematic errors in peak position. With Debye-Scherrer geometry for X-rays, you always have to consider how absorbing your sample is. And we'll talk a little bit more in a minute about absorption corrections for this geometry. Debye-Scherrer transmission is also a very simple experimental geometry with an area detector. It's quite easy to implement. So the positions of Bragg reflections in a powder pattern depend first and foremost on the wavelength of radiation that you're using and the crystallite phases that are present in your sample. Specifically, the unit cell parameters of the phase and the Miller indices of the specific crystalline planes determine where each Bragg peak is going to be located. But systematic errors, which depend on the geometry and also on the sample properties, can also be very important. We mentioned previously diffraction is an interference effect, and Bragg's law is basically just describing the conditions required for constructive interference between waves from adjacent planes. And if you rearrange Bragg's law, you can see how the calculated 2 theta position depends on the wavelength and on the d-spacing between those crystalline planes. And the d-spacing in turn will depend on the lattice parameters and the Miller indices of the diffracting plane in the crystal. Crystal plane representation in 2D can be a little difficult to visualize. I've tried to represent 3 different sets of planes, Bragg planes here, with Miller indices 0, 1, 0, 1, 1, 1, and 1, 2, 0. And we'll describe how you actually obtain those Miller indices on the next slide. Generally, the smaller the Miller indices of the planes, the larger the d-spacing, and the lower the 2 theta angle at which that peak will occur. And these things can be hard to see in 2 dimensions. Unfortunately, I have some cubes, but I didn't bring them that actually illustrate them with picture cubes, but I can show those to you later if you have trouble seeing this on the screen. It's worth refreshing how the Miller indices are derived. To obtain the Miller indices from a plane, you look at where the plane intersects each crystallographic axis and as a fraction of the basis vector length. Then you invert these intercepts and you scale them to the smallest possible integer values. And the d-spacing is a function of the Miller indices, and the lattice parameters is given here at the bottom. And there's numerous software programs and apps where you can input a unit cell and a wavelength to generate a possible list of Bragg reflections for your material. Generally, multiple crystalline planes are equivalent due to symmetry, and the number of equivalent planes increases with increasing symmetry. You can see at the top here that the 3 individual cubic planes are all equivalent planes that belong to the 110 family of cubic planes. In contrast, for the tetragonal cell at the bottom, where the A and B axes are equivalent, but the C axis is unique. The 110 and 11 bar 0 planes are equivalent, but the 101 plane is clearly non-equivalent. There are two main systematic errors in peak positions in Bragg-Brentano geometry. Sample displacement is probably by far the most significant because it occurs in almost every sample, but it can be minimized with careful sample preparation. You can see displacement can actually be a positive or a negative value. This plane of the sample can be above the sample holder, or it can actually be below the sample holder as well. Displacement can also occur in Debye-Scherrer geometry, and g.s.2 actually has a correction for capillary displacement that's programmed into it. And you can account for displacement pretty well with Rietveld refinement, but if it's really pronounced, the peak shift can actually make it difficult to properly do search match phase identification. And you might have difficulty properly identifying the crystalline phases in your material if you've got enough displacement. And sample transparency occurs when your sample is composed of very light elements. So it predominantly occurs with organic materials, and it has a sine theta dependence. Next, we'll talk about pattern intensity. And there's a lot of factors that contribute to the intensity of a powder diffraction pattern. The equation here for intensity probably looks a little intimidating, but when you go through the factors one by one, it isn't quite so bad. And you can tell based on the summation signs here, the groups of parameters that apply to the whole pattern, or global parameters, and the parameters specific to individual phases. And then there's groups of parameters that are specific to individual Bragg reflections within each individual phase. So we'll start out here by looking at the background. The background of a powder pattern is due to multiple phenomena. There's inelastic scattering, you get air scattering, you can get X-ray fluorescence from elements in your sample, detector noise, and there's other causes as well. g.s.2 has a number of pretty robust empirical functions for modeling the background. The Chebyshev polynomial in particular is generally very, very stable to refine the background, and it's a very good way to start. For samples with amorphous content contributing to the background, like this example right here, you could use what's called a Debye function, or you can even use an individual peak to model the background in that area of the pattern. And for really complicated backgrounds, sometimes the best approach is just to start with a series of fixed points and interpolate the background between those points. Next, we'll look at some of these other global parameters that influence intensities in the whole pattern, including the Lorentz-polarization correction and the sample absorption. So the Lorentz-polarization correction is a geometric parameter that incorporates a number of different factors based on the geometry of your instrument and also on the polarization of your incident X-ray beam. The book Elements of X-ray Diffraction by Cullity has an excellent derivation of the individual contributions to the Lorentz-polarization factor. Practically what this means using g.s.2 is there's a value in g.s.2 for the polarization, which is in the instrument parameters, and I've listed some of the typical values you would use here for different instruments, which range from 0.5 for an unpolarized lab instrument with no monochromator to very close to 1 for highly polarized synchrotron X-rays. And often you can refine these if you want a very precise value using a standard material as well. For Bragg-Brentano geometry, the most common lab geometry, there are two cases that we need to consider in terms of sample absorption. As long as the absorption and the sample thickness are large enough so that the sample seems semi-infinite, the absorption factor becomes constant for all angles, and you don't actually have to worry about it, which is case number 1 here. If the sample is fairly non-absorbing and too thin, the beam will penetrate through the sample, and the absorption will vary with angle. Basically, you'll end up with a different factor with angle, which is typically a situation you want to avoid. You want your sample to be semi-infinite, normally in Bragg-Brentano geometry. For capillaries in transmission, absorption is generally a complicated function of this factor mu r. And the value of mu r gives you an idea of how absorbing your sample is and whether you need to apply a correction during your analysis. If mu r gets too high, say above about 2.5, you might want to rethink your experiment. Perhaps using a smaller capillary, a higher energy of the X-rays, or even possibly diluting your sample with a light non-crystalline component. The Advanced Photon Source has an excellent absorption guide and also an absorption online calculator at their website right here. And I also have a standalone calculator, which I can send you if you email me. Next, we'll look at the overall parameters that affect each of the individual crystalline phases in a mixture. So the scale factor is an overall proportionality factor for each crystalline phase, and it can be used to estimate the relative crystalline phase composition of a mixture. The exact way the scale factor is parameterized depends a little bit on the Rietveld program. For instance, some Rietveld programs implement the scale factor in the way that's shown right here. Others actually incorporate the volume into the scale factor rather than having it separate. So there's slightly different methods and ways that it's incorporated into Rietveld software. The important part is that the scale factor is proportional to the quantity at the phase of the crystalline phase. And it's also important to emphasize that this equation will give you the relative crystalline phase composition if you account for all of the crystalline phases in your sample. But any amorphous content will not be accounted for. And there are various ways you can estimate the amorphous content, like adding a carefully measured amount of an internal standard into your sample. It's also worth noting the differences between the scattering of crystalline compounds are often compared by referencing how strongly the compound scatters compared to corundum, or Al2O3. And you can see here, silicon scatters much more strongly than corundum in a 50-50 mixture. So the strongest silicon peaks will actually be much larger than the strongest corundum peaks in an equal mixture of them. And semi-quantitative phase analysis can actually be performed this way using what's called the reference intensity ratio method. There's a number of different absorption effects that can influence reflection intensity. I'm not going to talk about all of them here, but I have put some references. The main one I want to mention in detail is what's called microabsorption, which is this bottom one. Microabsorption is basically a contrast between high absorbing and low absorbing phases in your mixture of compounds. And what happens is high absorbing phases, the X-rays will only see the surface of the particle. So they actually tend to be underestimated. And lower absorbing phases, the X-rays will see the entire particle, so they tend to be overestimated. This is probably the biggest obstacle to getting accurate phase quantification from powder diffraction data. There's a few ways you can mitigate this. One way is to make sure your material is very well ground or micronized to obtain the smallest possible particle sizes. Because the microabsorption depends on a factor mu d. In this case, this is actually the particle size rather than the grain size. Beatrice? 5 minutes, okay. You can use higher energy radiation with the synchrotron, which definitely helps minimize microabsorption. And the gold standard for microabsorption is probably neutrons. But of course, neutrons aren't always easy to access, similar to the synchrotron. And Brindley actually devised a strategy for calculating the microabsorption and correcting for it. It's not normally practical because you have to know the particle size of all the individual constituents. in your mixture. So implementing it most of the time is not really practical. You're better off trying to avoid it altogether. Finally, we'll look at the parameters that apply to each Bragg reflection in each phase, starting with the structure factor. So the structure factor links the various atomic parameters for each atom in your crystal structure to the intensity of each Bragg reflection. To calculate the structure factor, the contributions are summed over all of the atoms in your unit cell. And the site occupancy here is a fraction between 0 and 1, reflecting the average occupancy of an atom on that site position. And multiple atoms can substitute on a single site. Atomic scattering factors for X-rays drop off pretty rapidly with angle, which is why most of the most intense peaks appear at low angle in X-ray powder diffraction patterns. One benefit of using neutrons is that the scattering length for neutrons is relatively independent of scattering angle. So you get large peaks throughout your powder pattern. You can see for this terbium titanate compound, which crystallizes in a pyrochlore type structure, the strongest Bragg reflections in the PXRD pattern are basically finished by about 50 degrees, give or take. Due to the heavy atoms, this compound actually scatters X-rays pretty well. But for some organic compounds, you might observe almost no significant reflections beyond about 40 degrees with, say, copper radiation. But there are strong reflections in the neutron pattern well out past 100 degrees 2 theta. X-rays are very predictable. Light atoms scatter X-rays weakly, and heavy atoms tend to scatter X-rays strongly. Neutron scattering lengths are kind of all over the place, which makes them very complementary to X-rays in many cases. Not all cases, but many cases. Some atoms actually have negative neutron scattering lengths, like hydrogen, and deuterium is often substituted for hydrogen in neutron diffraction studies because of the large incoherent scattering of neutrons by hydrogen, which appears as background in your pattern. And vanadium actually has a scattering length that's very close to 0, so it's typically used as a sample container for neutron diffraction. There are minor differences in the X-ray atomic scattering factors with oxidation state. You can see here, for very low angles or very low sine theta over lambda, the scattering factors for vanadium 3+ and 5+ are a little different than for neutral vanadium. For most applications, using neutral atoms in Rietveld refinement is fine. The differences are minimal enough. For the most part, I normally use neutral atoms. The displacement parameter represents the vibrational motion of the atoms around their equilibrium positions. So it also causes intensities to drop off with angle, which is one of the reasons why many single crystal structures are obtained at low temperature. So two conventions are used for the isotropic displacement parameters, B and U typically. And there's a factor of 8 pi squared or 79 that can be used to convert between them. You always want to make sure you know what format the displacement parameters are used for in the program you're using. And GSAS uses the U values, which are typically on the order of 0.01. Crystals have equivalent planes, and the number of the equivalent planes depend on the Miller indices, which we talked about before, which is known as reflection multiplicity. And this needs to be taken into account in order to obtain the correct reflection intensities. This is normally all done internally by the software, assuming you've loaded the structure up correctly. And reflection multiplicity increases significantly with increasing symmetry. You can see here how a general HKL reflection in cubic symmetry can have up to a reflection multiplicity of up to 48. A number of different functions are used to describe the X-ray diffraction peaks, but the most common is called the pseudo-void. A pseudo-void function is just a mixture of Gaussian and Lorentzian components with a mixing fraction eta. The Gaussian component tends to be mainly due to the instrument, while the Lorentzian component tends to be mainly due to the sample, at least with X-ray diffraction. It's a little different with neutron. The plot here shows Gaussian and Lorentzian peaks with equal full width at half maximum and area. And you can see the tails of the Lorentzian peaks are much, much longer than the Gaussian. So with some practice, you can visually identify the dominant component of the peaks in your patterns. And the most common implementation of this pseudo-void peak shape is called the Thomson-Cox-Hastings pseudo-void. And it parameterizes things so that the Gaussian and Lorentzian full width and half maxima can be refined separately. As I mentioned on the last slide, the Gaussian components are mostly due to the instrument, while the Lorentzian components are mostly due to sample broadening. And that inverse cosine theta components, they tend to relate to size broadening, while the tan theta components tend to relate to microstrain broadening. And the last factor influencing individual Bragg intensities is preferred orientation or texture. It tends to get called texture if it's a design feature, and it gets called preferred orientation when it's a nuisance that you're trying to avoid. If you picture a single crystal for any set of Bragg planes, their orientation will be the same anywhere in your sample, or in that crystal. Conversely, if you've got an ideal random powder, sets of Bragg planes from individual crystallites will be randomly oriented and uniformly distributed in all directions. In between what you have are what are called polycrystalline textured materials, where certain crystallite orientations are preferred over others. And this is a particularly common issue with clay minerals that can often complicate their quantification. And preferred orientation or texture causes systematic deviations in the distribution of intensities for a random powder. The middle pattern here is a organic material called beta-tristerin. And beta-tristerin is a very long, skinny molecule, which crystallizes in a triclinic cell with one extremely long edge, over 50 angstroms. So in general, so even in a capillary, it tends to show some preferred orientation, even when you're rotating the capillary. In general, large 2D detectors make it a lot easier to study preferred orientation, and they also make it a lot easier to mitigate it and minimize it, because you can integrate the 2D pattern azimuthally around the entire pattern to average out your preferred orientation if you want to get rid of it. And there are a couple of different approaches to quantifying preferred orientation in powders. For really straightforward cases, with typically uniaxial cases, you can use what's called the March-Delazy model, which provides a decent description, and I've provided a reference here. And for more complicated cases, Bob has developed a generalized spherical harmonic description, which is very powerful for looking at complicated cases of preferred orientation. And I don't have time to get into these methods right now, but they're both implemented in GSASS2. So those are our factors that control the intensities in power diffraction patterns. And I'm just going to summarize quickly because we're running out of time. Hopefully this has given you a decent picture of some of the things we can do with powder diffraction and the main factors that are necessary for describing your patterns. It's important to emphasize that the Rietveld method is a refinement method. It's not a structure solution method, but tomorrow we will have a presentation dedicated to a crystal structure solution and what you can do if you don't have a starting model for your material. I'd like to thank a number of people who I've liberally used either their figures or their knowledge. That they've definitely helped to make this presentation a much better presentation. And I've just provided a few good texts here for powder diffraction. In particular, if you're starting out and you're not familiar with powder diffraction, the top text by Pacharski and Zavaldi is a very, very good place for people who want to learn more. And I don't know whether there's any time for questions, but.
Ooh, we have 1 minute for questions. Thank you, Joel. Any questions for Joel? Adam.
All right, so my question is, some of these really problematic samples, do you then tackle that with sort of pre-describing, I guess, the orientation, or do you try to work that out? I'm thinking about the clays. Often we would try to make the clays purposefully lie flat. To try, but does that go against what you want to do your powder diffraction?
Well, it depends. So If you want to use a full pattern description of them, ideally you'd really like to get them random oriented. That's one nice advantage of the 2D detector. So you'll see beamlines tomorrow with both 2D detectors, and we'll also be looking at our high resolution beamline on Brockhaus with a strip detector. The 2D detectors to some extent help to minimize a lot of that preferred orientation. Looks like Bob would like to say something to you.
I'll make a specific comment about that. Spinning the sample, rotating it in a plane or whatever it is one does on the Bragg-Brentano machine, integrating around the rings in a 2D image. What those things do is that they make the texture cylindrical, which makes it easier to model. It does not eliminate it, it makes it cylindrical.
Okay.
So you have to be a little careful about that. It's hard to make the cylindrical orientation go away. You can't do it. Those methods. It simply simplifies it, makes it more amenable to treatment by the model. So the best thing to do is to try to prepare the samples so
Yeah, yeah, can be really hard.
Any more questions for Joel?
When you work with, for example, a nitride material, that you have a superlattice, that is, you don't have the C5, how you can work with the Reid? Because you say that you need a pattern.
Yeah, so you have to have a starting model. Tomorrow we're going to talk a lot about methods for crystal structure solution. So I'm going to give you an introductory talk tomorrow, and I'm actually going to do a couple of quick demos as well as I go to just show you how a couple of different software packages work. So I'll give you an idea. And we can talk about that more offline as well.
3, 2, 1.